Hello everyone, this is Kalpana here. In this video we're going to solve a differential equation which is of Mdx plus Ndy equal to 0 form. So let's get going. Problem: solve 3x plus 2y square into ydx plus 2x times 2x plus 3y square into dy equal to 0. So this is of Mdx plus Ndy equal to 0 form, right? So for m equal to 3x plus 2y square into y, we can write this as 3xy plus 2y cube, and n equal to 2x times 2x plus 3y square. We can write this as 2 2s are 4, x into x square plus 2 3s are 6, x y square. Let's now check whether the given differential equation is exact or not. If dou m by dou y, that is partial derivative of m with respect to y, equal to partial derivative of n with respect to x, then we can say that the given differential equation is exact. Let's check. So we'll find partial derivative of m with respect to y, treating x as constant, right? We have m 3xy plus 2y cube, right? So here 3 and x are constants, and in the second term 2 is constant, right? So we can write this as 3x into partial derivative of y with respect to y plus 2 into partial derivative of y cube with respect to y, right? Which gives us 3x into derivative of y with respect to y is 1 plus 2 into derivative of y cube with respect to y is 3y square, which gives us 3x plus 2 3s are 6 y square, right? Now let's find partial derivative of n with respect to x, treating y as constant. We have n 4x square plus 6xy square, right? So in the first term 4 is constant, in the second term 6y square is constant, right? So we can write this as 4 into partial derivative of x square with respect to x plus 6y square into partial derivative of x with respect to x, right? This gives us 4 into partial derivative of x square with respect to x is 2x plus 6y square into partial derivative of x with respect to x is 1. This gives us 4 2s are 8x plus 6y square. So by observing these two, we can say that partial derivative of m with respect to y is not equal to partial derivative of n with respect to x. So the given differential equation is not exact. Okay, fine. Now coming to the problem. Given differential equation 3x plus 2y square into y dx plus 2x times 2x plus 3y square into dy equal to 0, considered as equation 1. Therefore equation 1 is not exact, right? And we can write the given differential equation as 3xy dx plus 2y square into y is y cube dx plus 2 2s are 4 x into x square plus 2 3s are 6 x y square. So you'll get dy here into dy equal to 0, right? Now from the first equation and third equation, let's write it together. 3xy dx plus 4x square dy plus, now write the remaining terms, 2y cube dx plus 6xy square into dy equal to 0. So now I'm going to take x common from the first two terms and y square common from these two terms. Okay, then I'll get x times 3y dx plus 4x dy plus y square times 2y dx plus 6x dy equal to 0. So that we'll get, or we can write the given differential equation of some x power a y power b into mydx plus nxdy plus x power c y power d into pydx plus qxdy equal to 0 form. Okay. Now here you're having x, right? X is nothing but x power 1. So we can write this x as x power x into 1 better. And this x can be written as x power 0, and this y 1 can be written as y power 0. Sorry. Here you're having x, right? This x can be written as x power 1 into, and this 1 can be written as y power 0, since y power 0 equal to 1, right? So we can write this x as x power n into y power 0. Okay, into 3y dx plus 4x dy plus, here you're having y square and you don't have any x term here, right? So we can write this as 1 into y square and just replace this 1 by x power 0, since x power 0 is 1. So I'll get x power 0 into y square. Now you can write this y square as x power 0 into y square. And the terms under brackets remains the same. Okay, see, now we have written the given differential equation to x power a y power b into mydx plus nxdy plus x power c into y power d into pydx plus qxdy equal to 0 form, right? Now consider this equation as equation number 2. Since the given differential equation can be written of this form, so here x power alpha y power beta will be our integrating factor. Okay, so here we need to find alpha and beta. Okay, we'll use the integrating factor to make the given differential equation to exact equation, and later we'll find the general solution to the equation, to the given equation, using the general solution formula of exact equation. Okay, let's see that. Now by comparing these two, we'll get the values of constants a, b, c, d, m, n, p and q. Okay, say equation 2 is of this form, where a equal to 1, b equal to 0, c equal to 0, d equal to 2, m equal to 3, n equal to 4, p equal to 2, q equal to 6. Right? Now x power alpha y power beta is our integrating factor, as I said you earlier. So now we need to find alpha and beta. Let's see that. Let x power alpha y power beta be the integrating factor. So we need to find alpha and beta here, right? We have A1, B0, C0, D2, M3, N4, P2, Q6. Now by using the formula A plus alpha plus 1 by M equal to B plus beta plus 1 by N, and C plus alpha plus 1 by P equal to D plus beta plus 1 by Q, we'll get two equations, and by solving those two equations we'll get the values of alpha and beta. Fine, let's now find the two equations. Substitute the values. A1 alpha plus 1 by B3, sorry, it's M equal to 3 for B equal to 0,
and n equal to 4, we'll get alpha plus 2 by 3 equal to beta plus 1 by 4, which gives us 4 times alpha plus 2 equal to 3 times beta plus 1, which gives us 4 alpha plus 4 2s are 8 equal to 3 beta plus 3 1s are 3. Now bring this 3 beta to LHS and take this 8 to RHS, we'll get 4 alpha minus 3 beta equal to 3 minus 8, which gives us 4 alpha minus 3 beta equal to minus 5. Consider it as equation number 8. Sorry, number A. Say. Now coming to the second formula, substitute the values of C, D, P and Q. We'll get 0 plus alpha plus 1 by P equal to 2 plus beta plus 1 by Q, 6. Which gives us alpha plus 1 by 2 equal to beta plus 3 by 6. 6 times alpha plus 1 equal to 2 times beta plus 3, or you can just write this as alpha plus 1 equal to 2 times beta plus 3 by 6, which gives us beta plus 3 by 3, right? Now we can write this as 3 times alpha plus 1 equal to beta plus 3. From this we'll get 3 alpha plus 3 equal to beta plus 3. Now bring this beta to LHS, take this 3 to RHS, we'll get, right? From this we'll get 3 alpha minus beta equal to 0. Consider as equation number B. Now we got two equations, 4 alpha minus 3 beta equal to minus 5 and 3 alpha minus beta equal to 0. Now by solving these two equations, we'll get the values of alpha and beta. Now we need to solve A and B, right? If you notice, in the second equation you're having beta, right? I'm trying to eliminate beta from these two equations. I mean by solving A and B. Firstly, I'll eliminate beta. So I need a 3 here. In order to eliminate beta, I need a 3 here. So what I'll do is I'll just multiply 3 to this equation. Now solving A and B, we get equation A will be as it is, and we'll multiply equation B with 3, so you'll get 9 alpha minus 3 beta equal to 0. Change the sign, so we'll get, see here, minus 3 beta plus 3 beta gets cancelled. 4 alpha minus 9 alpha gives minus 5 alpha equal to minus 5. From this we'll get alpha equal to minus 5 by minus 5, which is 1, right? Therefore alpha equal to 1. Now putting alpha equal to 1 in either of these two equations, we can find beta. Let's see for equation A. In equation A we have, right, or you can just write this as 4 alpha plus 5 equal to 3 beta. We'll just bring this minus 5 and take this to RHS. Okay, we'll just bring minus 5 to LHS and take minus 3 beta to RHS, then you'll get this. Now put alpha equal to 1. We'll get 4 plus 5 equal to 3 beta, which gives us 9 equal to 3 beta. From this we'll get beta equal to 9 by 3, which is 3, therefore beta equal to 3. Or if you want to substitute beta in the second equation, that is equation B, consider equation B, 3 alpha minus beta equal to 0. You can write this as 3 alpha equal to beta, or beta equal to 3 times alpha. We have the value of alpha, so put it. We'll get beta equal to 3. Finally, the values of alpha and beta are 1 and 3. Therefore, alpha equal to 1, beta equal to 3. Since alpha equal to 1, beta equal to 3. So our integrating factor will be x power alpha y power beta equal to x power 1 into y power 3, which is xy cube. Therefore, our integrating factor is xy cube. Now, equation 1 is reduced to an exact equation by multiplying it with xy cube. So let's multiply xy cube to equation 1. Multiplying 1 by integrating factor xy cube. 3x 2y square into ydx plus 2x into 2x plus 3y square into dy equal to 0. This gives us xy cube into 3xy plus 2y square into y is y cube into dx plus xy cube into 2x into 2x, 4x square plus 2 3s are 6 xy square into dy equal to 0, which gives us 3x into x square, y cube into y. See, bases are equal, so we'll add the powers. 3 plus 1 gives 4. We'll get y power 4 plus 2x into y cube into y. Bases are equal, add the powers. 3 plus 3, 6 into dx plus x, into 4 x square into x cube into y cube plus 6 x into x square, y cube into y square. Bases are equal, that is y. So we'll add the powers. 3 plus 2, we'll get 3 plus 2, 5 into dy equal to 0. Consider it as equation number 3, which is of mdx plus ndy equal to 0 form for m equal to 3x square y power 4 plus 2x y power 6 and n equal to 4x cube y cube plus 6x square y power 5. See, we have multiplied the integrating factor to equation 1 in order to reduce this equation to an exact equation. So, we got equation 3, right? By multiplying integrating factor to equation 1. Now, we have to check whether it is exact or not, right? So, if partial derivative of m with respect to y equal to partial derivative of n with respect to x, then we can say that the reduced equation is an exact equation. Okay? Obviously, it will be exact. We can see that now. Let's now find partial derivative of m with respect to y. For m equal to 3x square y power 4 plus 2x y power 6. Right? Here we need to find partial derivative with respect to y. So x is treated as constant. In the first term 3x square is constant and in the second term 2x is constant. So we can write this as 3x square into partial derivative of y power 4 with respect to y plus 2x into partial derivative of y power 6 with respect to y, which gives us 3x square into partial derivative of y power 4 with respect to y is 4 y cube plus 2x into partial derivative of y power 6 with respect to y is 6 y power 5, which gives us 3 5s are 12 x square y cube plus 2 6 are 12 x y power 5. Now, let's find partial derivative of n with respect to x. For n equal to 4x cube y cube plus 6x square y power 5. So here we need to find partial derivative with respect to x. So y is treated as constant in the first term, 4 y cube is constant, in the second term 6 y power 5 is constant. So we can write this as 4y cube into partial derivative of x cube with respect to x plus 6y power 5 into partial derivative of x square with respect to x. This gives us 4y cube into partial derivative of x cube with respect to x is 3x square plus 6y power 5 into partial derivative of x square with respect to x is 2x, which gives us 4 3s are 12 x square y cube plus 6 2s are 12 x y power 5, right? Now by observing these two, we can say that the partial derivative of m with respect to y equal to partial derivative of n with respect to x equal to 12x square y cube plus 12x y power 5, which says that equation 3 is exact. Therefore, partial derivative of m with respect to y equal to partial derivative of n with respect to x, which says that equation 3 is exact. So we have reduced the given differential equation to an exact equation. Now we'll find the solution, the general solution to equation 1 by finding the general solution to equation 3 using the general solution equation. The general solution formula of an exact equation. Let's see that. The general solution to an exact equation is given by integral y mdx, integral mdx treating y as constant plus integral terms of n free from x into dy equal to c. So we'll find each integral separately for our convenience. I'll begin with the first one, integral mdx treating y as constant. For m equal to, now we are going to find the general solution to the reduced equation 3. Okay, for m equal to 3x square y power 4 plus 2x y power 6 into dx. So here we need to treat y as constant. In the first term y power 4 is constant, and in the second term y power 6 is constant. Also 3 and 2 are constant. So we can write this as 3 y power 4 into integral x square dx plus 2 y power 6 into integral x dx, which gives us 3 y power 4 into integral x square dx is x cube by 3 plus 2 y power 6 into integral x dx is x square by 2, right? So 3 gets cancelled and 2 gets cancelled. This gives us x cube y power 4 plus x square y power 6, right? So the result obtained from the first integral is, therefore, integral m dx treating y as constant equal to, fine. Therefore, integral m dx treating y as constant equal to x cube y power 4 plus x square y power 6. Now coming to the second integral. Integral terms of n free from x into dy. So now observe n. So in both the terms we are having x, right? So there is no such term of n which is free from x. So integral of terms of n free from x is 0. The result obtained from the second integral is 0. Now coming to the general solution to equation 3. Therefore, the general solution to an exact equation 3 is given by integral m dx plus integral of terms of n free from x. Result obtained from the first integral is x cube y power 4 plus x square y power 6 plus result obtained from the second integral is 0 equal to c, which gives us x cube y power 4 plus x square y power 6 equal to 0. Equal to c. Now if you notice, we can take x square common from these two terms and also y power 4 common from these two terms. So let's take x square y power 4 common, then you'll get x square y power 4 into x plus y square equal to c. Therefore, the general solution to the given equation is x square y power 4 into x plus y square equal to c.
Well, we have seen a problem from differential equation in this video using x power alpha, y power beta and integrating factor. I hope you'll understand. We'll see you in the next video. Until then, bye bye.